This is the first section of the traveling salesman problem. It's an introduction to Hamilton circuits and Hamilton paths. Okay, we'll start off with some definitions here. Hamilton path is a path that visits each vertex of the graph once and only once. A Hamilton circuit is pretty similar, except, of course, at the end we've got to go back to where we started. So we end at our starting vertex. This is It seems like a similar concept to Euler circuits, but it's actually going to be very different. In Euler circuits, we were going along edges, so you're counting the edges and paying more attention to those. With the Hamilton circuits, you're just paying attention to the vertices. It doesn't matter how many edges you go through, or it doesn't matter that you go through all of them in this case. So you find that this chapter might be a little bit easier than the Euler chapter because we just have to hit each vertex instead. Alright, so the best way to really illustrate these differences is by example. Figure A, so here's our first one. It shows a graph that has Euler circuits, and I'm going to trace this for you to show you. So if we were to say start at F, and think back to Euler circuits now in the previous chapter. So from F to A to D to G, C, back to D, E, A, B, E, C, B, and then F. Alright, so we've traced all edges in this case, and again, that's with Euler circuits or paths. You are focusing on the edges. So let me get rid of this really quick. But notice that there's not an Euler path. So with Euler circuits and paths, there can only really be one or the other. So if we have a circuit, there's not going to be a path available because there are no odd vertices on the graph. But let's talk about Hamilton circuits instead. With Hamilton circuits, all we have to do is hit every vertex. So if we restart at F, for example, okay, it doesn't matter that we hit all the edges. We just want to hit every single vertex. So we start at F, and we'll go over to A. So we got A done, A to D, D to G, G to C, C to E, E to B, and then back to F. So there's our Hamilton circuit. And if we just wanted a path, we could erase that little part from B to F and just end at B. Notice again, we haven't hit all the edges, we've just gotten all the vertices, and that's all that matters with the Hamilton chapter. Okay, another example here, figure B. We have a graph that has no Euler circuits, but does have Euler paths. Okay, so for example, if we were to start at C and go to D, and then E, B, A, D. So we've hit all of the edges, but there is no way we can create a circuit out of this, specifically because of the odd vertices in here. So vertices D and C. D has 3 edges and C only has 1, so no circuits possible. And this also has no Hamilton circuits. So let me erase this really quick. Okay, because sooner or later you're going to have to go back to C, and let me show you what I mean by that. So if we were to start at C and then go to D, E, B, A. Okay, so we've hit all the vertices, but to get back to C, I would have to hit D a second time, so that wouldn't work. Let's try it again just to make sure here. Maybe start at B. Okay, so go to E, D. Alright, here's the problem. I could go to C or go to A, but sooner or later I'm still going to have to go back to D. So I could go to C, but then back to D, so that won't work. Or I could go to A, but I have to go back to D if I wanted to go over to C, so that wouldn't work either. But this one does have a path, so, and I think I did it earlier without talking about it. For example, if we were to, no, I started at C earlier. If we were to start at A, you could do A, B, E, D, E. And again, you must go along the edges that are provided. Sorry, D, C. Ends at C. You don't have to go back to A. So we can have a path but no circuit in this case. Alright, figure C. We have a graph that has neither Euler circuits nor paths, so not possible specifically because we have too many vertices that or too many odd vertices. So A, B, C, and D are all odd vertices. But has Hamilton circuits and actually has paths as well. So for example, if we have A, B, C, D, E, I'll trace that really quick. So A, B, C, D, E. Okay. Oh, and then A. So there's a circuit and there's a path. Okay, so typically with the Hamilton stuff, if we have a circuit, we're going to have a path, because to create a path instead of a circuit, all we really need to do is take away that last trip traveled on that last edge, AE, and we just have a path instead. Okay, graph D. So figure D shows a graph that has Euler circuits. The vertices are all even, so we know we're going to have an Euler circuit that's possible, and has no Hamilton circuits. So no matter what, and here I'll illustrate this. For the Euler circuits, you could probably start anywhere actually. So start at A, go A, E, D, C, E, B, A. Alright, so that's going back to Euler. We hit all the edges, so that's good. But with Hamilton, so for instance, if we try to start at A, okay, if I go A, B, E, D, C, okay, so I can't go back to A unless I go through E again. Okay, so E's it's kind of like that bridge point. We must go back to get to where we were. But it does have a path, so if I just erase what I just did, actually, notice that we've hit all the vertices and we just end up at C, so the A, B, E, D, C. So that one works for a path. Alright, graph V. We have a graph that has no Euler circuits but does have an Euler path. So remember, in Euler circuit, you got to pass through every edge and come back to where you started. Not possible because of the odd vertices F and G, but we can create a path there. So if we were to start at F, go to B, A, D, E, B, C, D, G, and that's not the only way you can do it, but that's one of the solutions for the Euler paths. Let's see, get rid of this really quick. So notice that this one has neither a Hamilton circuit nor a Hamilton path, okay? And we can try, so let's see what happens here. We start at F, we go to B, maybe to A here, D. We can choose C, but we'd have to go back to B, or we could choose E, we'd also have to go back to B, okay? So that wouldn't work. Maybe try somewhere different this time. So if we try, maybe we start at E, somewhere in the middle. So D, C, B. Okay, so vertices like F and G can cause problems with these, because if we go to F, there's no way to get back except going back to B. And then we could go over to A, but that wouldn't work. So remember that major difference between Hamilton circuits and paths and Euler circuits and paths. With Euler, you can go back to vertices that you use because we're concerned with covering all the edges. But with Hamilton circuits, you cannot reuse vertices. Okay, and last example is figure F here, and I'm sorry, this paragraph is actually wrong here. It says that it shows a graph that has neither Euler circuits nor Euler paths. I think that part's correct. So F and G and D and B, yeah, there's too many odd vertices for either circuit or Euler path, a circuit or a path for the Euler stuff. But this part about neither Hamilton circuits nor Hamilton paths, sorry, I think there's some kind of typo there, or I put in the wrong picture, but we'll just work with the picture that we have. F, let's see, if we were to start at F, we could actually go from F to B to A to E to C to D to G pretty easily. We've hit all the vertices. So there is a path available. So we have a Hamilton. Let me just and just erase that. So we do have a Hamilton path. So that works for this. But a circuit will not work, and the reason for that being F and G out there all alone. Again, we can try, maybe start somewhere different, somewhere like C, and get a different color there, somewhere like C to E to A to B, but if I were to go to F, I'd still have to come back to B. Same thing down here. Maybe if I started at G, there's no way I could do the whole thing without coming back to D to get back to G. So just a path for this example. Okay, and here's just a summary. Just kind of ignore F over here. That wasn't the same picture that I used. Sorry about that. But the first 5 that we did, we have a chart. And notice the answers for yes and no are kind of all over the place. There's really not much of a correlation happening between Euler paths and Hamilton circuits and paths. So to kind of sum that up, just because an Euler path or circuit exists on a graph, that doesn't really mean that we're going to have any kind of Hamilton path or circuit. So they're not really related at all. So it wouldn't be a good idea to try to look for Euler circuits or paths if you're doing a problem that has to do with the Hamilton chapter. So they're very different. There are some theorems though that make this chapter a little easier. So if I want to find out whether or not there is a Hamilton circuit or path, just use, for example, Dirac's theorem, and we can easily say yes or no. So that theorem is if a connected graph has n vertices, so n number of vertices, which needs to be more than 2, by the way, so 3 or more, and all of them have degree bigger or equal to n divided by 2, so half of that, then the graph has a Hamilton circuit. And I'm just going to draw out an example here for you. So let's say we have vertices, we'll say A, B, C, and D here. Okay, and they're connected like this. We'll cross these up too. Okay, so let's see, if a graph has n vertices, so we have 4 vertices, so we've satisfied the first part, and all of them have degree bigger or equal to n divided by 2. So n in this case would be 4, so 4 vertices, and then 4 divided by 2 is just 2. So, and each of these vertices has degree 3, which is more than 2. So we know somewhere on here we're going to have a Hamilton circuit, that it's definitely possible. So, for example, we could start at A and go to B, and then go to C, and go to D, and then we could go from D back to A.